In these next few sections, we're going to be looking at how to calculate the vapor pressure of a solution. And in doing this, we're going to apply an equation that's called Raoult's law. And in this case, we're going to be looking at different situations. So how to calculate the vapor pressure solution depends quite a bit on the properties of the solute. And in this case, there's 3 different cases that we're going to be looking at. All the calculations are going to look very similar, but we have to treat these 3 differently, and they all have to do with certain characteristics of the solute. So the first one is a nonionic non-volatile solute. So these things are like sugar, caffeine, fats, and proteins, something that will dissolve in water, but they're not volatile in themselves. So if you take sugar and you leave it out on a desktop or something like that, it doesn't evaporate. So the idea here is once we dissolve this nonionic non-volatile solute, it will not create a vapor pressure in itself. So all that's left to create a vapor pressure is the solvent. And that's kind of what Raoult's law says, that as we add in a solute to our solvent, the vapor pressure of the solvent will decrease. And we'll look at that when we actually do some calculations. So the solute in itself is non-volatile, so it does not create a vapor pressure. So the only thing creating a vapor pressure is the solvent. Also, because it's non-ionic, we don't have to worry about it dissociating. So there's no I value involved, so no Van't Hoff factor. The next type is ionic-nonvolatile solute. So the same as before, this because it's non-volatile, it will not create a vapor pressure in itself. So the solute will not add to the vapor pressure of the situation. The only thing that is creating a vapor pressure is our solvent. And just like before, Raoult's law says that the vapor pressure of a solvent is going to decrease as we add a solute to it. So the only thing that we need to consider now is, because it's ionic, we have to consider the Van't Hoff factor I. So as it disassociates, it's going to have a slightly more impact on the vapor pressure calculation. So we need to include I inside of our calculations. So examples of an ionic non-volatile solute are salts like NaCl or NaOH. And like with NaCl, we need to take into account that this is going to dissociate into 2 actual species, Na plus and Cl minus. And so that's going to have an effect of our calculation of the vapor pressure of our solution. So the last one is actually a non-ionic volatile solute. So in this case, because it's volatile, the solute is actually going to have a vapor pressure in itself. So the same thing, the solvent is going to have a decreased vapor pressure. That's true, but one of the things that we need to do is also include the vapor pressure of the solute. So now we have 2 different things creating a vapor pressure. So in this case, the solvent will be creating a vapor pressure and the solute will be creating a vapor pressure. And we're going to apply Raoult's law in both situations. So in order to find the overall vapor pressure, we need to combine these 2 vapor pressures together. Because it's non-ionic, we don't have to worry about an I factor here. So all of these calculations will involve Raoult's law. So all these calculations will involve the same equation, but there's going to be subtle differences depending on the type of solute that we have. So Raoult's law says that the vapor pressure of a solution is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. So this is the idea that as we dissolve things into our solvent, the vapor pressure of the solvent is going to decrease. That's because the mole fraction is going to become less than 1. So overall, Raoult's law says that as we dissolve solutes into our solvent, the vapor pressure of the solvent tends to decrease. So the vapor pressure of the solution is expected to be less than the vapor pressure of the pure solvent.